Welcome to the Mathematical Finance course. In this lecture, we are going to see the method of deriving the Black-Scholes formula, which is of utmost importance in the theory of option pricing. So the plan of my talk is, first we will derive the related model, that is the model which has its relation with stochastic model as well as Black-Scholes formula. Next, find the expected value. From that, derive the solution of that model, and how will you express it in the form of Black-Scholes formula. Now consider the portfolio. So first we have to derive the model based on the portfolios. Consider the portfolio pi suffix naught and pi suffix g. So portfolio is nothing but it comprises of all the investment, either in the shares or stocks or currencies or any other bonds like that. So here we are assuming that the portfolio at any initial time 0 consists of shares and cash alone. So let it consist a number of shares at time t equal to 0. At that time S suffix 0 is the value of the stock and B is the amount in hand. After some time t, in case of the cash, if it is invested with the risk-free interest rate of R, it grows exponentially in the form B into e power RT. Whereas in case of shares, it depends upon the price of the stock at the time t. Hence, pi suffix g is expressed as a s suffix t plus b into e power RT. From that, we have to derive the model. Now, again rewrite the model. Just multiply by e power minus RT on both sides. Now you are getting this equation. On the left hand side, you get a relation between the portfolios. On the right hand side, between the price of the stocks. Take the expected values on both sides. If I assume that the expected value on the right hand side vanishes, then obviously the expected value on the left hand side also vanishes. Since I have to create a model that relates the portfolios at the initial time and the final time, the expectation of e power minus RT pi suffix t minus pi suffix 0 should be equal to some constant, that is equal to 0. Now taking the expectation for pi suffix t and pi suffix 0. Here expected of e power minus RT into pi suffix t minus expected value of pi naught. Expected value of pi naught is equal to pi naught. Hence finally we are left with the relation pi naught equal to e power minus RT into expected value of pi suffix t. If I know the value of pi suffix t, it is possible for me to find the value of the portfolio at the time t equal to 0. Now with respect to that A, so that's most important, it should vary along with time. If it varies along with time, then the model will be preserved. So the model will act in the right way if A varies over time, otherwise there will be a problem. Now since our aim is to find the stock model, replace the portfolio with the stock pi naught by S naught bar and pi suffix t by st bar. On solving this, we using the known formula S suffix t equal to S naught into e power sigma bt plus mu minus sigma square by 2 into t. So this is the solution of geometric Brownian motion. We arrive at this relation. And so the expected value of e power sigma bt plus m minus r into t should be equal to 1. And hence the model is S suffix t bar equal to S naught into e power sigma bt plus mu minus sigma square by 2 into t. Mu refers to the drift term, sigma volatility, b suffix t refers to the Brownian random variable, and S naught the stock price at the initial time. So the above model that you have derived is nothing but a geometric Brownian motion model. So that is the solution of the geometric Brownian motion model. As I already told you, the Black-Scholes formula is also a solution of geometric Brownian motion. In other words, the above derived model can be related to geometric Brownian motion, whereas Black-Scholes formula can also be related to geometric Brownian motion. Now we have to find the relation between these two, the model and the Black-Scholes formula, since both of them are related to geometric Brownian motion. So first, let us see the advantage of the above derived model. This model is impractical because the growth rate will be very low. If I apply that model, the growth rate will be very low. So no one will invest if the growth rate is low, obviously. But it has its own advantage. It is suitable for computing the current value. For calculating the current value, it can be used. But for calculating the future value, it cannot be used. Hence, we move on to the next form. That is the Black-Scholes formula. So for that, let us assume the call option. At some time t, let S suffix t be the price of the option, price of the stock, whereas x is the exercise price. We will exercise that particular call option only if we get the profit. That is, the difference between the stock price on that time must be greater than the exercise price. Then only it is possible to exercise the call option. So assume that it has profit. Therefore, we can exercise that option. Now, taking the expected value. I want to take the expected value. What is the need for taking the expected value? Since we already told you, you have to use the model that you derived in the previous part. You have to use that model. That's why you have to take the expected value. And another one thing, the most important thing is, you have to replace the Brownian random variable. That's most important. B suffix t should be replaced. So it should be replaced by a normal random variable. As you know, it has most applications. Most of the applications of probability theory will be through normal random variable only. It can be applied anywhere. It has vast applications. So anyway, so capital Z can be used here. You have to use standard normal random variable. Mean 0, variance 1. Capital Z can be used instead of B suffix. So rewrite the option V equal to, so Z root 2 into Z minus X, ST minus X. Instead of ST, substitute that relation minus X. What by the definition of expectation of X is equal to integral minus into plus infinity 1 by root 2 pi X into f of x dx. Use that formula here in the equation number 3. But here the interlimits is from minus infinity to plus infinity. But we know that all the variables here should be non-negative. Since this is a real world application problem, everything must be non-negative. Therefore, you have to find the value for which st minus x is positive. Must be greater than 0. Then I have to find some value for x. Let small a be that value, which gives non-negative solution. So that we will see the value of that a in the last slide. Now you have to find the integral values. Split the integral into two parts. Minus x into as one integrand and the remaining thing as another integrand. So e power minus rt into I plus j. Find the value of I. Here we have to use the substitution process as well as the property of normal random variable. Capital N. N of a is equal to 1 by root 2 pi into lower a to infinity e power minus x square by 2 dx. That is the formula. You have to apply that formula here. So n of minus a 1 by 2 pi into lower a to infinity e power minus x square by 2 into ds. Similarly for j you have to use the same thing. And finally we are arrived at the value v equal to s naught n of minus of a minus sigma into root t as x into e power minus rt. Capital T refers to the time until expiration n of minus a. Here a and n of x is defined. S naught into n of d1 minus e power rt x into n of d2. This is the Black-Scholes formula. This is called as the Black-Scholes formula. So which can be used for pricing the future values of any option. X is the strike price, sigma is the volatility, and R risk-free interest rate. Here, the parameters should be treated as a constant, as I already told you. Since you are considering the Brownian variable as the normal random variable and using the parameters, constant parameters, it is possible to find the deterministic solution. That's why you are using this Black-Scholes formula. So more details on this Black-Scholes formula and its applications can be studied once the Black-Scholes model is derived. It is Black-Scholes formula. If we derive the Black-Scholes model and based on that it is possible to derive the applications of all these relations. So as mentioned, what you have studied here is how to form a stock model using the portfolio values with known portfolio values, applying the practical conditions. So instead of Brownian, you have to use normal conditions. That is, for practical purpose, you are applying those conditions and finding the expected value of the model. And finally, deriving the Black-Scholes formula. As I already told you, this is the most important formula in the theory of option pricing. So thank you.